So let's enter the world of the nearly infinitesimally small. Well, maybe that is a bit of an exaggeration for those used to the nano world. I think few audiophiles and many designers of tone arms, cartridges, and turntables don't fully appreciate how small the undulations are that are in the groove that we can actually resolve through the groove. So let's look at this small world and let's look at the anatomy of the stylus and the cantilever that is meant to trace what's in those small grooves. Alright, so first let's discuss the groove content. Lathes are capable of putting down undulations in the groove that we can ultimately resolve through headphones or speakers that can be measured in the sub-micron range very easily. I've seen various research that try to determine what the smallest physical amount of deflection is necessary for you and I to be able to hear something that's in the groove. And they don't all agree with each other, but I can safely say that it would be in the low triple-digit nanometer range. Now, a nanometer is a millionth of a millimeter. In fact, the wavelength of light is about 350 nanometers. So we're talking about undulations in the groove that we can hear that are actually too small to see with an optical microscope. Now, when you consider this tiny little world, you can appreciate how important it is for us to be able, if we care to hear everything in the groove, to trace all of these bits and pieces that are laid down in the track and do so very faithfully, without allowing the cartridge to modulate the tone arm, or vice versa. So here's a photograph we took on our lab microscope of an Ortophon test track, specifically the higher frequency portion of the frequency sweep track. And in order to get this image, we tilted the entire microscope at 45 degrees so that we would image only one channel of the V-shaped groove. What you see here is an image of the left channel groove, and on the left is the bottom of the groove, and at the right would be the land of the record, the surface of the record that we all touch. You'll notice that there are these undulations going throughout the groove wall. These undulations are effectively mechanical sine waves. These are the frequency laid down in the track. If you measure the distance from peak to peak in this image, you will see that there's only 11 microns between each full cycle. This particular track is cut 135 millimeters from the center of the record. If this same signal were cut at the innermost modulated groove of about 60 millimeters, the distance between these peaks would more than halve. So you can imagine why a conical stylus with a 25 micron radius wouldn't even be able to get into these undulations and see the bottoms of each of these valleys. And you can keep in mind that the undulations that you saw carved into that groove in that last photograph were made at a rather high amplitude, perhaps louder than we would normally get from a musical record. So they're rather large features. Alright, now let's turn our attention to the stylus cantilever assembly. If you've watched my video on zenith error, you know that there are only really 3 manufacturers in the world of stylus cantilever assemblies. And they make those same stylus cantilever assemblies that your cartridge manufacturer used in the assembly of your cartridge. So you'll see in this image of a couple stylus cantilever assemblies that on the far left is the tiny feature that is the stylus, right on that far left tip. That's of course attached to these cantilevers, and the cantilever is attached to the coil former, around which the coil of wire is ultimately wrapped by the cartridge manufacturer. And behind the coil former is something akin to piano wire that acts as the pivot around which the stylus cantilever assembly rotates. A special note about the coil former, the one you see in that photograph, was square shaped, but they can also be made in a cross-like pattern. Either way, they make a good shape around which to wrap wire and create the coils that, when they move in the magnetic flux field in your cartridge, will throw off an electrical signal. Now that you've seen this coil former and its relationship to the cantilever, it will be helpful for you to see our video on azimuth and why we only will use an electrical signal and never an optical alignment in order to adjust the cartridge on its azimuth axis. All right, now let's talk about the stylus and the anatomy of it. So if you've got a fine line contact stylus, and I hope you do because it's the only way to get all of the information out of the groove, you'll have two radiuses on this stylus that you'll have to be concerned about. This is an image of the stylus taken from the front. And if you look carefully on either side of the tip of the stylus, you will see that there is what is called the major radius. For a fine line contact stylus, this is usually anywhere from 90 microns down to about 50 microns in radius. And so the purpose of this major radius is so that when you align the cartridge for optimal channel crosstalk on the azimuth axis, the stylus can actually ride in the groove at an angle like this, and because of the major radius, it will contact both channels of the groove properly. The next part of the stylus to be aware of is the minor radius. In this picture, you will see the stylus from the side profile, and the ridge at the very tip is the minor radius. The purpose of this minor radius, right here, is to mimic the shape of the cutterhead stylus. The cutterhead stylus has a minor radius of its own of about 2 microns, and a good fine line contact stylus will have a minor radius as little as 2.5 microns or up to about 4 microns. When this minor radius on your fine line contact stylus is aligned perfectly in the groove, in the same manner in which the cutterhead stylus was aligned in the groove, you will get maximum information from your musical signal. For more information on this, refer to our video on zenith error. So if the ultimate goal is to transcribe the groove in the same manner in which the cutterhead stylus created the groove in the first place, then we're, of course, have to ask, how was that cutterhead stylus aligned? There are 3 alignment parameters that the cutterhead stylus is aligned with. Those 3 alignment parameters are azimuth angle, rake angle, and the radial line pattern, which for purposes of this video, let's just refer to as zenith alignment. So for 2 of 3 of those parameters, it's not debatable what the cutterhead stylus should be aligned at. For azimuth angle, it should be perfectly perpendicular to the surface of the lacquer. For the radial line pattern, that cutterhead stylus should be on the collinear line of the lacquer, not to the side of it and not diagonal to it. Well, for the rake angle of the cutterhead stylus, there isn't one size fits all. It kind of depends on which engineer you're speaking to. From what I understand, most of them cut at 90 degrees, but there is something called springback, which would change the effective goal for playback. More on this in the future. Here are a couple images of a cutterhead stylus. From the front, you'll see that it is a 90-degree angle, and it cuts the channel with a sharp chisel shape. It is heated as it is dredged through the lacquer and pulls out the chip, which is sucked away by a vacuum hose. Just like playback styli, these cutterhead styli are made within tolerances, are not always perfectly symmetrical, and do have errors of their own. So in addition to analyzing your cartridges for optimal playback angles and understanding the angular relationship between your stylus and cantilever assemblies, we are now also taking to analyzing cutterhead styli, because they are often not cut symmetrically. And we can choose the cutterhead styli that are the most symmetrical, which allow for the quietest grooves to be cut and grooves that have no crosstalk built right into the groove. For more information on how to achieve those 3 optimal angles for your cartridge, please refer to our video library on the WallyTools YouTube channel or our WallyTools website at wallyanalog.com. And there it is. Enjoy analog forever.